Yeah, so I'm Micah, and I'm a third year PhD student at Berkeley. I work with Anka Dragan and Stuart Russell. And I've mostly been working on like human AI systems broadly, like human AI collaboration. And now I'm mostly focusing on like recommender systems and incentives for user manipulation when you're using reinforcement learning. And this that I'm going to present today has nothing to do with all of this. So it's like it was an internship project that I did at Microsoft, or like we did together at Microsoft like a year and a half ago or so. But then it took a while to, I guess, bring to like fruition. And it's basically about trying to, unifying inference and sequential decision problems. So it's kind of like in the line of work of decision transformer, trajectory transformer, but kind of generalizing that type of paradigm. So, okay, let's see. So so I'm sure you're all familiar about how.
Just got it.
Oh, whoops.
You just hit it on the board, okay? Yeah, or like literally touch the big screen.
Touch the big screen. Wow. Okay, that's fancy. Nice. Okay, well, I'm sure you're all familiar about how, like language, like treating language as a sequence modeling problem has been very successful in NLP. So you kind of like separate out words and like assign them tokens essentially, and then you stick everything into a transformer, and then you try to predict stuff. So for example, BERT. You train it like, or one of the objectives is a close objective that is basically masking out some of the inputs and then trying to predict or like fill the blanks in the. And this is what BERT does. And there's previous work. I don't know what's going on here, but hopefully it's fine. So anyways, previous work has treated even like sequential decision problems as sequence modeling problems. So you can think about like states, actions, rewards, and how they, I guess, relate to one another, right? Like how do future states tend to correlate with previous states and actions and so on, and rewards and so on. And you can like stick this into a big transformer and try to predict, high reward actions in the future. So this is kind of like what decision transformer and offline or like trajectory transformer did. And what we try to do is kind of like building on top of that kind of intuition. Can we also like apply this kind of principle of masking that is like, that's been quite successful in NLP, even to sequential decision problems. So what that means, or what that would look like is, okay, let's like mask some of these inputs and then feed this like masked input or masked sequence of states, actions, and rewards into a transformer, and then try to predict the missing tokens in the input, right? So why would one do that? Why would one do this? Well, let's just consider this one prediction of output, right? So it's like I'm giving it a model like the first states and first couple of states and the initial action, and then I'm trying to predict the next action based on this input, right? And I guess like if you're familiar with sequential decision problem literature, you'll probably recognize this as being, well, I mean, like first of all, an inference, like you're inferring action one based on like state 0, action 0, and state 1. But this is like corresponds to behavior cloning in some sense. So it's like the objective of behavior cloning. It's like, given this data set that you have, what's the probability of the next action given the context we have so far? And one thing to note is that, like there will be multiple maskings that correspond to behavior cloning depending on how long of a context length you have. So, I mean, you can predict the first action, like you can train your model to predict the first action given the first state at time step 0, and then train your model to predict the second action given the current history at time step 1, and so on, right? So I guess like one thing that I'd like to stress is that for every type of masking you can have for your input, there corresponds like a specific inference task that you're trying to perform, right? So every type of masking of the input sequence that you feed into the model will correspond to an inference. And so let me switch to this kind of like more compact notation where essentially everything that's masked, like, I mean, the stuff that's in white is the stuff that's masked. And then these kind of like more shaded regions are what we're trying to predict based on like the inputs, that is the stuff that's not shaded. Okay, so I guess like the main advantage, or one of the biggest advantages of like thinking of these or thinking as inferences as maskings, is that you can represent a vast, basically any inference you can think of in a sequential decision problem just as a specific masking scheme of like what you're masking in the input and what you're trying to predict in the output. So yeah, you can represent behavior cloning, as I was just saying a second ago, but you can also represent reward conditioned imitation or like offline RL. So this is kind of like what decision transformer and trajectory transformer focused on by basically just adding into the input like some kind of like reward to go token and then training like that. And I guess also at test time, setting a specific reward to go that you want, and then querying actions that lead to that kind of reward. And you can also represent stuff like goal conditioning. So like it's very naturally lends itself to say, okay, let's just unmask the last time step state, and then let's make predictions about actions based on the last time step state that we want, right? And there's many other things you could do, like waypoint conditioning. So you just like unmask specific waypoints that you want your agent to reach as you go along, and then sample actions based on these like conditions. Yeah.
Does that all have hats on it?
Yeah. So what decision transformer does is that they don't use rewards directly. They use reward to goes. So reward to go is basically the sum of the rewards from that point of time up until the end of the trajectory. And the reason is because like they want a test time. So if you train with reward to goes like this, at test time, you can set a reward to go that you want. And that basically captures how well the whole trajectory is, like, or how good the whole trajectory is, rather than just the transition. So yeah, I guess like, yeah, they would train with like, a bunch of random data, say, and then you like at test time, you request a high reward or high return to go. And supposedly the network should be able to generalize a bit outside of the data distribution and like give you a better performance than the demonstrator that you had. Yeah, so it's kind of like a offline RL via supervised learning, essentially, or RL via supervised learning. Yeah, that's related to like upside down RL. Yeah, I don't know if, yeah, but cool. So anyway, so you can do these kinds of like tasks that are like, I guess, these seem like relatively sensible, but you can also do like more like, I don't know, stranger tasks too, if you want. So you could just say, let me input only the final state and the final action, and let me try to, infer what the initial part of the trajectory was, or you could like try to infer like entire missing portions of trajectories if that's potentially useful in your type of setting. So I guess, yeah, I'll talk about that in a second, but yeah, we could try to infer the future, like the entire future of a trajectory just based on the beginning. And like with a whole distribution of states and actions, I guess, or you can also represent tasks like forward dynamics or inverse dynamics just by maskings. Okay, so intuitively, yeah, like this type of framework enables you to specify a bunch of different tasks just as like maskings, and without doing any weird things to your model, except for like how you're masking your inputs. So it's very flexible in that way. And yeah, I guess like, yeah, I've already talked about most of these. Yeah, so for example, past inference, you could say, well, what's one potential usage of using past inference? You could say, well, if I have a crash at my last time step, how could I have reached this crash condition, at the end? And it's like you get the distribution over potential trajectories that could have led to that bad state at the end. Say. Okay, but there's multiple other inferences, or like, I mean, of like a vast number of inferences that can also be represented in this framework that I haven't listed here. These are just like some examples of things you might care about in like normal and like sequential decision problems. Okay, so I guess like one question that kind of like emerges from having this type of framework is, how should I be training my model? So there's multiple ways one can go about it. You can just train on a single task, say like you're interested in doing behavior cloning. You can just apply the maskings to the sequences that you have in your training data that correspond to the behavior cloning task, essentially. So you're just randomly masking stuff in your input according to the behavior cloning type of format, right? And you just train in a supervised learning, of course, like manner in this way. Another thing you could do is, well, you know, like given that the only thing that we need to do to train a model that does multiple things at once is just vary the maskings. Well, you know, we can just sample a masking from any one of, you know, n tasks that we care about and a training time, and then just train the model on all of these masking types at once. So at the end, you would get a single model that's able to, you know, do behavior cloning, offline RL, and predict inverse dynamics or something. Okay, so, but I guess like another approach that you could try that is a bit more extreme in some sense is just training on like random maskings, like we're applying random maskings to your input. So that's a little bit ridiculous because it's kind of like equivalent to training a single model on like all possible inferences that could be expressed in this sequential decision problem. And why is that? Well, because like any one of these tasks that we were talking about before have some chance of occurring during training time when you're sampling your masks, right? Because if you sample your masks just by chance in a behavior cloning fashion, then you know, okay, that behavior cloning is in distribution for the training of your model, right? So in a sense, any inference is in distribution for the training of your model, and your model will learn how to deal with these different maskings to perform the different tasks. And I guess like, yeah, one thing that we didn't test, but I'm quite certain of, is that it's actually learning to generalize across the masking space too. So even if you didn't ever show it one specific type of masking at training time, I'm pretty sure that it would do a decent job at like performing that inference at test time, even though it's never seen that specific type of masking. Just because like in the types of experiments we've been running, like I guess there's like, I think tens of millions of tasks or like impossible inferences that can be like, yeah, represented. And so I think like, yeah, I'm guessing during training time, like most, like a lot of them only occur like once or something, or probably not much more than that. Yeah, so anyways, another question is, oh yeah, sorry.
Do you do weighting on these tasks?
No. Yeah, so, or I guess like, so for the random masking setting, so yeah, so it's like, so it's not quite just the most naive type of randomization where each mask has got 50% chance of being switched on or off. Like we did one small change that like improved the performance like a decent amount. That was we first sample uniformly from 0 to 1 a masking probability for an individual sequence, and then we mask each token with that probability within a single sequence. So what that changes is that it makes it more likely to have sequences where almost all the masks are not present or almost all the masks are present. And why that matters is because a lot of the tasks that you might care about, like behavior cloning or something, like you use a lot of the time with like almost all the stuff unmasked except for maybe the last action, or vice versa, like you're just sampling the first action given the first state. And that would be very unlikely to happen if you're just sampling each individual mask with like 50% chance. Yeah. But yeah, it's basically, it's almost like a naive randomization of the maskings. Yeah, so there's no like weighing for like specific tasks, say. Okay, so yeah. Another thing that one can do is like, okay, so you have this kind of like random pre-training type of paradigm where you can pre-train with like random masks. Well, I guess like this lends itself pretty naturally to this kind of paradigm of like first you pre-train with random masks and then you fine-tune further on a specific, you know, task of interest if you're interested in that. So for example, yeah, you could fine-tune on behavior cloning or on offline RL and potentially obtain better you know, performance. So I guess like this is what we investigated in the paper, or like trying these different training regimes out and see how they perform relative to one another. Yeah, so I guess like one advantage of using like, or just training with this randomized masking is that if you have a model that was pre-trained with randomized masking, like it should be able to like 0-shot perform all of the tasks. Like it's like you just put the masking that you want and it just does goal conditioning or, you know, reward conditioning or something. But then, yeah, you can potentially improve performance further and have a single task model when you fine tune it. Okay, so yeah, so one of the experimental setups that we consider is like this kind of like pretty simple mini grid environment. there's like this agent that needs to pick up a key and then open a door and go to a goal location. And yeah, so the agent and like the key are randomly initialized. We have like different sizes of data sets where like the agent is like trying to perform this task, but like makes some mistakes. So like there's like randomness in the data set. And we have different data like size regimes. And yeah, so like we chose this task just because it was like simple enough to like do a bunch of experiments in and like do a bunch of runs without like, I don't know, it being like super computationally expensive, but also being complex enough for like demonstrating all of the various tasks that we want to show. Like, I don't know, like it's pretty clear what waypoint conditioning means in this domain, and it's like meaningful in some sense, or like, you know, past inference or something. Okay, so I guess first of all, the thing that we found is that, yeah, it is possible to train a single model on random tasks or on all tasks. And like sometimes it even works better than just training on a specialized, like on a like if you're interested in a single task, it might be better to just train on all tasks and use that zero shot rather than training a specialized model. So that was like kind of surprising. And in general, yeah, like what we saw is that, yeah, we can train a single model and then just by changing the masking, get it to do behavior cloning as you would expect, or like do some kind of goal conditioning trajectory or sample reward condition trajectory, waypoint condition, then like or sample even a backwards inference trajectory. Yeah.
So is the data for the training is it an offline data set or are you collecting the data offline?
So this is all offline data. Yeah.
Do you have any like rewards for opening the door or obtaining the key?
No. Yeah, it's just like the reward, I think, is just like how close you get to the goal state. Yeah. So it's like, yeah.
And is that distance just measured on that grid?
Yes.
So it's not dependent on like whether the agent has key or not.
No, it doesn't. Yeah, it's not dependent. But yeah, I guess like to get a certain distance to the goal, you must get the key and open the door, or otherwise you can't reach, like you can't get past the door. Yeah. Cool. Yeah, so I guess like, yeah, you can get a single set of weights that performs all of these different tasks, I guess, at once in some sense. Yeah, and you can do also kind of like strange things that generally, like, I guess, yeah, specialized models wouldn't really enable you to do. So this is kind of like, if you give the model as input, like these three states, you can make predictions about what the distribution over the states was in the missing time steps. So I guess if you start out at this in this position and then you're here 2 time steps later, so there's like 2 time steps missing here, then the agent must have gone like either up, left, or left, up, right? And so, okay, sorry, I guess like I can start from this. And I guess in this case, it gets like some kind of distribution over, you know, the agent either went up or it went left. Here it's got a little bit of probability mass on this box too that is incorrect. But and I guess here it actually gets it kind of incorrect too. But in this case, it works pretty well. So I guess let's just look at this for a second. So here, like the agent must have gone right, up, right, or up, right to get here 2 time steps later. And we see that I guess in this case, it managed to learn the correct distribution over like the intermediate states. So I guess it's not infallible in the sense that, yeah, this distribution makes no sense. Like the agent must be either here or here. But yeah, I guess like you can do these types of inferences too with the same model that was used to, you know, get the rollouts and so on, just by masking things appropriately. Okay. So I guess like, yeah, one question that I guess, yeah, we were particularly interested in is like, how do the various training regimes compare to using specialized models? So like, if you just care about doing well on goal conditioning, like, should you just train a goal condition model, or is it advantageous to first kind of pre-train with random maskings and then fine tune, or just only do the pre-training and using it as a model directly? So this graph is like maybe a little bit hard to read, but the main thing to keep in mind is, or I guess like the main thing that is helpful to understand it is that when like basically all of the columns have been normalized column-wise, and they're all validation losses. So it's like, I guess like kind of measuring how good the predictions are. And if you see a value of 1, that's like the best model. And then all the other values are kind of like percentage, how much percent worse is it? So this is like 4% worse than this model. So it's like if you train on random masking and you like evaluate on reward conditioning, the best paradigm is to use random masking and then fine tuning. And then, I don't know, just doing random masking is 4% worse, essentially, than if you do this fine tuning step. So you can get 4% better by doing the fine tuning, essentially. And when compare to the specialized models, one can look at this diagonal. So basically, the diagonal entries correspond to training on a specific task and evaluating on that specific task. So it's like, okay, I train on behavior cloning, I evaluate on behavior cloning. That actually turns out to be the best model. But say like goal conditioning, if I train on goal conditioning and I evaluate on goal conditioning, that's like actually 10% worse than if I do this random mask pre-training and then do the fine tuning. And I guess like in about half of the cases, even just looking at random masking directly ends up doing better than like specialized models. Yeah.
So I noticed the column for dynamics has a lot of big values.
Yes.
Why is that?
Yeah, so I guess like we like talk about this more in the paper, but I would mostly ignore that column. Like I think it's due to like some just peculiarity of the environment, that the forward dynamics are deterministic, and so like it's very easy. Like basically all the loss values are extremely small. And so, I don't know, it's very easy to be like, you know, many orders of magnitude smaller than like other methods. And it's mostly just a function of training time rather than, I don't know, actual learning. So yeah, I would mostly just ignore it. Yeah.
I want to also talk about the difference of like computation involved.
Yeah. So I'll talk about that in a second. Or I mean, I guess like, yeah. Maybe not in depth as I should, but like you can look at the paper if you want more details. Yeah, but yeah, I guess like in general, as you would expect, training with random maskings is like more computationally intensive than training specialized models. And the main thing, like just on a high level, is that if you train specialized models, they tend to overfit much faster. So like they reach like, you know, minimum loss, like validation loss pretty quickly and then start overfitting. While like training on randomized masking, like the loss continues going down for a very long time, because you're kind of like, I guess, yeah, training on a bunch of different things. Yeah, like I guess the validation loss on a single task, say like just if you're interested on goal conditioning, like the validation loss will continue going down because as it trains on all of these different tasks, it gets marginally better at goal conditioning. But like I guess it overfits much less, I guess. Yeah.
Is this similar to dropout or variation of dropout? Sounds like heuristically.
Yeah, I mean, I think like there's definitely some like conceptual similarities. I think like the main thing that is cool here in my mind is that like it's not just dropout for dropout's sake. Like having these maskings on the input space not only improves the training, but also unlocks other types of tasks that you like. Every masking corresponds to a task, right? While in dropout, like, okay, if I drop out some random stuff, like doesn't correspond to a task. I'm just making stuff harder for my network to learn, right? So in a sense here, you're getting for free the fact that, you know, you can do both behavior cloning and reward conditioning and goal conditioning just from this principle of like, let me mask some stuff out and like, maybe that will improve representations or like, you know, yeah. Yeah.
How much is this teaching you like more training data than compute optimization?
Sorry?
So maybe using like more training data and compute.
Yeah, so we tried, so all of these models are all trained on the same amount of training data. Like the only thing that's different is like how you're doing the masking training time, right? So like in a sense, like I guess the intuition there is that the random mask model is like making better use of the limited training data you have because it's masking, like you're using the masking to kind of like do some kind of data augmentation almost, or you're squeezing out more information about the environment because you're using the same trajectory masked in one way to, you know, predict inverse dynamics, and then you're reusing that trajectory masked in a different way to do, you know, behavior cloning. And that kind of like forces your model to learn more things about the environment than if you were just training on behavior cloning, say. But yeah, so I guess, yeah, so in terms of like amount of training data, it's the same. And then compute, like, I guess the amount of compute required is different for the different models. But say that you trained everything with the same amount of compute, like this is a graph that you would get. because like all of the specialized models after a certain point, like they start overfitting. So you're just wasting compute, right? But yeah, if you do early stopping, like, yeah, I mean, that's what we do here. Like we do early stopping, and like the models do reach their lowest validation loss point much faster than like the random masking models. But that's just because they're learning one thing rather than, 10 million or something. Yeah. Yeah. Cool. Okay, yeah. So we also like compared to using neural networks, or like basically what if you don't really need to do, don't really need transformers to do masking on the inputs, right? You could just mask out random parts of the inputs with just a big neural net. It turned out that, yeah, I guess like as maybe one would expect, transformers are pretty important to get like better performance in these types of tasks. So like if you do the same thing, like where you do random masking with neural networks, it's like, it tends to be a decent amount worse, like, I don't know, about 20–30% worse or even more, depending on the task. And we also compared to decision transformer, and like we see that, I guess, yeah, at least our fine-tuned, like random masking plus fine-tuned is definitely better than decision transformer. And like, I guess, I guess some of the cases, yeah. And yeah, and this is also like taking into account the fact that decision transformer is using like a GPT type architecture that is supposedly better at generation. So I think, yeah, I don't know, there's some directions of future work of how, like, I guess UniMASK could be improved by using GPT type architectures rather than like BERT. And that I think that should like basically increase the gap between the two methods. Yeah.
Did you also do random masking and fine tuning?
So no, we didn't try the fine tuning part. Yeah, but I guess like the results for the random masking were looking sufficiently bad that like we didn't think it was worth trying. But it's relatively easy to set that up if you're interested. Like all our code is like available and stuff. Okay, yeah. So I've already kind of mentioned that. And yeah, I guess like, yeah, I've kind of also talked about this. Like we use the same amount of data. Why does like random masking do better than like specialized models of like, and like, especially when you do fine tuning? Like mostly it's just this fact of like, yeah, less overfitting. So this is kind of like training curves for like a specialized model where you see that already like within 1 million time steps, you're like reach the minimum and then you start overfitting. But instead like the random masking training kind of just continues, like the validation loss for the waypoint conditioning task, for example, just continues kind of going down for a long time.
Yeah, that's what happened to dropout as well.
Yeah. So I mean, I guess that, yeah, that doesn't surprise me. Like in a sense, I do think they're like pretty similar in terms of like probably the mechanism of how, yeah, I think like the mechanism of why dropout would work is probably very, very similar to why this would be advantageous too. Yeah. Okay, so yeah, it's some kind of like data augmentation effect or like that improves representations. Yeah, and we try this with like multiple different amounts of data too. So it's like, oh, you train it on like 50 trajectories, 500 or 1,000, and you kind of see the same type of trends across like multiple data regimes. So I don't know, I guess that seemed like, it seemed to happen like robustly, I guess, across different data regimes.
Do you get 1,000 trajectories? The environment's so small.
Yeah, so I guess like, so what we wanted to try with 1,000 trajectories was like, if you have coverage of like basically all possible trajectories for the most part, like do you still get this effect up here, where you do like randomized masking and then fine tuning and it improves things. And, it seems like it, like, I guess these are actually probably the best, like, I mean, depending on how much you want to look at this specific value, like for behavior cloning, there's the task that we struggle with the most. Like the randomized masking plus fine tuning here is like the closest to the best model than in the other ones. Yeah.
It seems strange if it's seen everything. It would do better with masking.
Right. Like, I guess like, yeah, I do think that there's something like, yeah, I'm not sure. Like, so I guess like, I don't know if you actually see everything. Like, I guess like, that's a good question of like, I don't know, investigating exactly like how much coverage you have, like, because there is like a lot of, like, I mean, I'm pretty sure, I don't know. Yeah, I guess one would have to look at exactly how many trajectories are possible in this domain. Like, I'm pretty sure they're like quite a lot because you can make mistakes and go back like multiple time steps in a row.
Oh, so they're not perfect.
No, they're not perfect trajectories.
Oh,
Yes, yes, yes. So there's like it is a pretty large space, but like I don't know if like with 1,000 trajectories you're like covering like 90% of it, or like like 50% of it, or like 100% of it. I doubt it's 100, but like I don't know how close you are to that. But yeah, I also found that kind of counterintuitive. That like like I was expecting that once you add more trajectories, like the effect would become smaller because of this kind of like data augmentation effect, but doesn't seem to happen. And yeah, I don't really have a strong sense of why. Yeah.
Do you anticipate that the quality of demonstrations matters at all, or if this result?
I mean, I guess like, let's see. So I mean, like for the most part, I don't think so. Like, or I guess like, I mean, the quality of the demonstration matters a lot for like, reward conditioning. Because I don't know, if you want to be able to generalize to better rewards, like you should have like good, or I mean, I guess maybe a diversity of rewards. I don't really know like what the latest in the offline RL literature is in terms of that. But I guess like in terms of like the quality of the, like for behavior cloning, I don't see why having, very high quality or like lower quality trajectories should really change things by much, or it seems like these effects should be kind of independent from that. Like, I guess if you have like perfectly deterministic trajectories, that definitely changes things because it's easier to go off distribution and so on. But yeah, I think like for most regimes, it shouldn't really matter too much. Yeah, or I would expect the same effect to hold. Yeah, and like even the specialized models would suffer from like perfectly deterministic trajectories. Yeah. Okay, and then another environment that we considered is like a non-Markovian maze 2D environment that's kind of like a harder version of the maze 2D environment, where you have like a dot that needs to go like navigate to another point in the maze, and they're like randomly initialized. The state is just the continuous location of the self, I guess, and the goal location that you need to reach. And the actions are like continuous accelerations in a 2D box. And yeah, and the reward is like how much distance you've covered towards the goal. Yeah, and one thing that we found, like we started doing experiments in like the D4RL environments, but we found that it was like very easy, or I mean, relatively easy for the policies to just kind of like memorize, even like with very little amount of data, like how to act in the environment. And sorry?
Like memorize a fixed path.
Yeah, basically, yeah. So even if you have like, like very few trajectories, like I think even like 5 trajectories or something, we were able to get like pretty high rewards. And so like all of the methods, like, I mean, all the methods that we're considering, we're all getting like pretty high rewards, even like with like basically no data. So it didn't seem very informative. And we talked to the people that like, I guess did the decision transformer work, and they were also saying that I guess D4RL wasn't a very informative benchmark. So I guess at that point we decided to scrap it and like kind of use this. It was like, I think, harder in like important ways. So for example, it's like non-Markovian, like the expert is non-Markovian, and like that kind of justifies more why you would even want to use a sequence model, because if your expert is Markovian, then you don't need a sequence model to perfectly match the expert, or like so anyways, so yeah, the expert is non-Markovian. The state, we removed the velocity components from the state. So like to be able to tell what velocity you're going at, you need to also see like the history of like, I don't know, or basically reason about the history of your past positions and kind of like impute what velocity you are going at to select an action well. And yeah, and that's it. Okay, so I guess like we tried various types of regimes here too, and I guess like we only considered two tasks here. So it's behavior cloning and reward conditioning, and we measure like the rewards rather than the validation losses. And we see that in this case, actually doing multitask, like so basically just training on behavior cloning and reward conditioning rather than training on everything, and then doing fine tuning, leads to better performance for the most part than doing the random mask plus fine tuning. So I think this is like, I don't know, scratching or I don't know, I guess it like, how do you say it? Like, I guess it suggests that maybe doing randomized masking is a bit too extreme in some domains, because you're actually training on like too many tasks, and that can like definitely hurt your performance. Like eventually, like it's clear that if you're training on like, a very large context window, say, right, where you have like an exponential increase in the number of tasks that you should be able to perform, like your model will struggle to basically learn, like, I mean, even contain enough mechanisms to be able to do these like trillions of types of inferences that you're asking it to do, right? So randomized masking, just like as we do it, is maybe like a bit of a, I guess, naive way of approaching it that might work for like shorter context lengths, but then we'll struggle to generalize to like larger context lengths. So I think, yeah, future work should definitely investigate how to structure better like the types of randomizations that you want to use in order to kind of like focus the model's attention on learning in ways that, like, I guess are useful. So they kind of like form useful auxiliary tasks, but also aren't just like, you know, like completely random tasks that have no help for learning and just like take up kind of like space in the model for doing these types of like useless inferences. Okay, and then and so we see that like with larger context lengths, this type of effect kind of like, I don't know, probably it worsens the performance of the model. And then I guess one thing that we also do here is, we baseline against decision transformer, and we see that, we do a lot better than decision transformer. But then we took some of the insights from, like, I guess our approach of like how we, so we made some modifications on top of decision transformer in addition to using the masking, and in addition to switching to like this BERT model rather than a GPT model. And I guess like we took some of these modifications that you can see in the paper and added them to the decision transformer type of paradigm, and we saw that you can basically recover a lot of the performance just by using this modified, GPT model that is like, or decision GPT model that is basically our modified decision transformer. Yeah.
I must have missed this. These are rewards, right?
Yeah, these are rewards. Yeah.
Oh, returns.
Sorry?
Returns.
Returns. Yeah, these are trajectory returns. Yeah.
And how do you, because I guess when you are applying, you're trying to either like minimize the equivalent log or anything. How do you also solve the control problem? And like, do you optimize that model for?
So you're optimizing just to reduce the loss,
right.
But then once you have that, you can auto-regressively sample actions in the environment, like as a behavior cloning model, right? And then we just look at the returns that you get just by auto-regressively evaluating the model in the environment. Yeah. Cool. Yeah. So I think I've mostly talked about this. And yeah, I guess like in terms of limitations, like the tasks are relatively simple, the context lengths are relatively short. And yeah, like future work should like scale up to more complex domains and like potentially use decoder only models. So that's like kind of GPT models that have been shown to be better at generation rather than like, I guess like, yeah, BERT, I guess is like considered to be much worse at generating sequences. Yeah.
If it's not bidirectional, how would you do that in this?
Yeah, so I guess like there's this thing called like prefix LM, or like there's a trick to basically do that. I'm happy to talk more about that later. And I guess like exploring alternate randomization schemes that are more targeted seems like, I don't know, I guess fundamental to like scale up to longer context lengths. And maybe explore, I don't know, multi-agent applications. Like I think there's a lot of things that are interesting if you have multiple agents and you're like trying to say, make inferences about other agents based on like some agents' behaviors and stuff like that, or like portions of trajectories of other agents, and like what does that mean for most likely other agents' actions and stuff. So I think that's like a cool kind of direction. And yeah, it's very easy to test things out. Like the code is available and it's like relatively well structured, I hope. And yeah, so just in conclusion, UniMASK is a framework that enables to flexibly define and train model which naturally represent inference tasks and support multitask training. And it allows a single random mask or multitask pre-trained model to perform any task, zero shot. And you can also additionally improve performance on individual tasks by fine-tuning further, I guess, this pre-trained model. Yeah, cool. And thank you all for listening.